A spinning wheel resists being tipped over. You know this. Anybody who has ever held a bicycle wheel by the axle and spun it knows this. You feel it pull against your hands. It fights you. It wants to stay in the same plane. And so naturally, when somebody asks you, why does a bicycle stay upright, you say, well, the wheels are spinning. That is a gyroscope. The gyroscopic effect keeps it balanced. Case closed. And you feel good about that answer. You feel like a person who understands physics. Because the word gyroscope sounds like physics. It sounds like you have explained something. And the beautiful part is, it even seems to check out. A bicycle that is standing still falls over. A bicycle that is moving stays up. What changed? The wheels are spinning. There you go. Gyroscopic precession. Done. That is completely wrong. And I can prove it. Not wrong in the fussy, nitpicking way where a professor says, well, technically, no. I mean wrong in the deep sense. Wrong in the sense that if you took the gyroscopic effect away entirely, a bicycle would still stay upright. Wrong in the sense that a very clever group of engineers actually built such a bicycle, pushed it down a hallway, gave it a shove sideways, and watched it recover all by itself. No gyroscope. No rider, no trick. Just a bicycle that is not supposed to work, working fine. So what is really keeping it up? Let me take you through this the honest way, because the real answer is one of the most surprising things in classical mechanics. And it has been hiding right under our noses, between our legs, on every ride to the grocery store, for about 150 years. Let us start with what the gyroscopic story actually claims. Because I want to be fair. The people who believed this were not stupid. They were very smart. Some of them were among the best mathematical physicists in Germany. So let us give them their due. A gyroscope is any object that spins. A top, a flywheel, the earth for that matter. When you spin something, it gains what we call angular momentum. Angular momentum is a vector. It points along the axis of rotation. And it does not like to change direction. That is the key property. You have to apply a torque, a twisting force, to change the direction of that angular momentum vector. And when you do, the object does not tilt the way you pushed it. It precesses. It turns sideways, 90 degrees from where you pushed. This is real. This is solid physics. You can demonstrate it in 10 seconds with a bicycle wheel and a piece of string. Hang the wheel from one end of the axle. When it is not spinning, it flops down. When it is spinning, it does not fall. It slowly rotates around the string. Precession. Gorgeous. Every physics teacher has done this demonstration. So the story goes like this. When a bicycle leans to the left, gravity is applying a torque. That torque tries to tip the spinning front wheel over. But because the wheel is a gyroscope, it does not tip. Instead, it precesses. And the direction of that precession happens to be exactly the direction you need the handlebars to turn. It steers the front wheel into the lean. The bicycle curves to the left. That curving motion generates what you might loosely call a centrifugal push back to the right. The bicycle straightens up. Balance restored. And look at how many things seem to confirm this. A bicycle standing still has no spinning wheels and falls over. A bicycle going fast has rapidly spinning wheels and stays up. A unicycle is harder to balance than a bicycle. And what does a unicycle have? A smaller wheel with less angular momentum. A child's bicycle with small wheels is harder to ride than an adult's bicycle with large wheels. More angular momentum, more stability. Everything lines up. If you are a physics teacher, this is the explanation you give on a Friday afternoon when a student asks an interesting question and you have 4 minutes left in class. It is crisp, it is elegant. It uses a concept the students just learned, and it seems to explain the observations. What more could you want? I will tell you what more you could want. You could want it to be true, elegant, satisfying, and every step of the logic is correct, in isolation. Each piece is real physics. The problem is that the whole story put together is not why the bicycle stays up. The gyroscopic effect is a real force. It does contribute. But it is a small contributor, much smaller than people think, and you can remove it entirely without the bicycle noticing very much. How do we know? Well, the first hint came almost 90 years ago, though it took decades for anyone to follow up on it. In 1910, two of the finest mathematical minds in Germany, Felix Klein and Arnold Sommerfeld, published a massive treatise on the theory of the gyroscope. These were serious people. Klein had reshaped geometry. Sommerfeld would go on to train more Nobel Prize winners than any other physicist in history. In their treatise, they devoted an entire section to the bicycle. They analyzed the Whipple equations, and they concluded that without the gyroscopic effect, a bicycle could not be self-stable. This was taken as gospel for decades. Klein and Sommerfeld said so. Case closed. Except they were wrong. Their analysis was correct for the specific bicycle parameters they tested, but they generalized too broadly. They assumed their particular example was universal, and it was not. The first real experimental challenge came from a British chemist named David Jones. In 1970, Jones published a paper in Physics Today, and I have to say it is one of the most delightful papers I have ever read. The man set out to build an unrideable bicycle, not a broken bicycle, not a bicycle with no wheels, a bicycle that looked normal, mostly worked normal, but had one specific feature removed, so that it should, in theory, be impossible to ride. His first target was the gyroscope. He called his creation URB1, Unrideable Bicycle Number 1. He took a regular bicycle and mounted a second front wheel alongside the first one, slightly off the ground so it did not touch the pavement. He rigged it to spin in the opposite direction of the regular wheel, counter-rotating. The two wheels had equal and opposite angular momentum. Total gyroscopic effect, 0. Cancelled. Gone. He climbed on, pushed off, and waited to crash. He did not crash. He rode it, hands-free. Down the road, around the corner, no drama at all. Jones wrote that it felt slightly different, slightly odd, as if something subtle had changed in the texture of the ride. But he could balance on it without any trouble. No hands on the handlebars, no death grip, just an ordinary ride on a theoretically unrideable machine. Think about what that means. If the gyroscope were the main reason a bicycle stays upright, removing it completely should have been catastrophic. You would expect the bike to collapse under you like a folding chair with a broken hinge. Instead, you get a bike that feels maybe 2% different. The gyroscope was contributing, sure, but it was not doing the heavy lifting. Whatever was keeping that bicycle upright, it was something else entirely. Jones was thrilled and frustrated at the same time. His unrideable bicycle was perfectly rideable, so he went back to the workshop. URB2 was an attempt at something different, a caster wheel mounted directly in line with the steering axis, but the caster overheated and could not handle road bumps. Inconclusive. Abandon that line. URB3 was more interesting. He reversed the front fork so that the wheel's contact point was farther behind the steering axis than on a normal bike. He was trying to exaggerate what engineers call the trail, the distance between where the steering axis meets the ground and where the tire actually touches. And he got a surprise. This bicycle, instead of being unstable, was ridiculously stable, almost too stable. When he pushed it with no rider, it ran on and on for dozens of yards before falling over. It was more stable than a normal bicycle. He had accidentally made it better. By this point, Jones understood that the trail, this business of where the front wheel touches the ground relative to the steering axis, was far more important than the spinning wheel. He went after it directly. He finally built URB4, with the front wheel mounted about 4 inches ahead of its normal position, giving the bicycle severe negative trail. And this one actually worked, or rather it did not work. When he pushed it forward with no rider, it toppled almost immediately. Smashing success. in the sense that he had finally created a machine of absolutely no utility whatsoever. His words. But here is the important nuance. Even URB4, the one with the wrong trail, could still be ridden by a person with hands on the handlebars. It was terrible. It was scary. But a human rider could compensate. The trail is important for self-stability, for the bicycle's ability to balance without a rider. But a skilled human can overcome even a bad trail design. So Jones established two key things. The gyroscope is not necessary for human-ridden stability. And the trail is important for riderless stability, but not strictly necessary for ridden stability. These are different claims, and people have been confusing them ever since. Now let me tell you about the trail more carefully, because it is actually closer to the truth, even though it is also not the whole story. Look at the front fork of any bicycle. The steering axis, the line around which the handlebars rotate, is tilted backward. It does not go straight up and down. It leans toward the rider. If you extend that line all the way down to the ground, it hits the pavement at a point that is in front of where the tire actually touches. The distance between these 2 points, the distance the tire contact trails behind the steering axis, is called the trail. Why does this matter? Think about a shopping cart. Those little wheels on a shopping cart are mounted behind their pivot point. That is why they swivel around to follow wherever you push the cart. The wheel is always trailing behind the axle. It self-aligns. The front wheel of a bicycle does the same thing. When the bike leans, the trail creates a force that tends to steer the front wheel in the direction of the lean, just like a caster follows the push. This is a real effect, and it does contribute. But is it necessary? Is it the thing that makes a bicycle rideable? Jones tried to find out. He built bicycles with different amounts of trail. He built one with extra trail, where the contact point was way behind the steering axis. That bicycle was absurdly stable, almost too stable. It did not want to turn. Riding it felt like wrestling. Then he built one where the contact point was in front of the steering axis, giving it what we call negative trail. This reversed the caster effect. Instead of self-aligning, the wheel should actively try to steer away from the lean. Should be a disaster. And it was hard. That bicycle was tricky. With no hands on the handlebars, Jones could not stay up. He had found something important. The trail seemed to matter more than the gyroscope. But notice what I said. He could not ride it no hands. He could still ride it with his hands on the bars. A human rider, with hands on the handlebars, could compensate for the wrong trail. So the trail is a factor. It contributes. But a skilled rider can overcome its absence. At this point you might be thinking, all right, so it is the trail, not the gyroscope. Mystery solved. But that is not right either. Because 4 decades after Jones, a team of researchers in the Netherlands built a machine that proved the trail is not necessary. In 2011, a group from Delft University of Technology in the Netherlands, working with Andy Ruina at Cornell University, published a paper in the journal Science, one of the most prestigious scientific journals in the world. And what they did was extraordinary. They did not just build another unrideable bicycle. They did something more rigorous. They started with the mathematics. Using the full Whipple equations of motion, all 25 parameters, they asked a precise mathematical question. Does there exist any bicycle design that has zero gyroscopic effect, negative trail, and is still self-stable? They ran the equations through a computer, searching through the vast space of possible bicycle geometries. And the equations said yes, such a design exists. So they built it. And it looked strange, very strange. Not like a bicycle at all, really. It had tiny wheels, about the size of saucers. Each wheel had a counter-rotating disc attached to it, spinning in the opposite direction, so that the total angular momentum of each wheel assembly was 0. No gyroscope. The steering geometry was arranged so that the front wheel contacted the ground slightly in front of the steering axis. Negative trail. By every traditional theory, by every textbook explanation, by every popular science article ever written about bicycle balance, this thing should not work. They named it the two-mass skate bicycle. TMS for short. They rolled it down a hallway. It balanced. They gave it a sideways push while it was rolling. It wobbled, corrected itself, and straightened out. Above a speed of about 5 miles per hour, it was reliably self-stable. They filmed it in slow motion. They measured the lean angle and the steering angle with precision instruments. The measured behavior matched the theoretical predictions from the equations. The paper landed like a small earthquake in the engineering community. For decades, people had argued about gyroscopes versus trail. This paper said, "Forget both. Neither one is necessary. Something deeper is at work." So now we have eliminated both of the popular answers, and the bicycle still works. What in the name of physics is keeping it up? Let me tell you what I think is the deepest truth about this problem, and it is something most people never get to. A bicycle is not a static object in balance. It is a dynamic system in a constant state of falling and recovering. It never sits perfectly upright. It is always leaning, always correcting. The question is not what holds it up. The question is what makes it steer into the fall. Because that is the trick. That is the whole trick. And once you see it, you cannot unsee it. When a bicycle leans to the left, if the front wheel turns to the left, the bicycle will curve to the left, and that curving will push the top of the bike back to the right. It is the same physics as when you balance a broomstick on your palm. You do not hold the broomstick still. You keep moving your hand under it. Wherever it starts to fall, you scoot your hand in that direction, and the base gets back under the center of gravity. Try it sometime. Stand up, put a broomstick on your palm, and keep it balanced. Watch what your hand does. It never stops moving. It is constantly chasing the top of the stick, making small corrections. Left, right, forward, back. The broomstick is never truly balanced. It is always falling. Your hand is always catching it, and the longer the broomstick, the easier it is, because you have more time to react. A short pencil on your fingertip is almost impossible. A tall mop handle is easy. A bicycle does the same thing with its front wheel. When the bike leans left, the front wheel steers left. The base, the contact patches, scoot left. The center of gravity ends up back above the support. Then the bike overcorrects slightly, leans a little to the right, the wheel steers right, and the whole dance continues. It is a constant, elegant wobble. The bicycle is a broomstick that moves its own base. A skilled rider does this deliberately, adjusting the handlebars to keep the center of gravity over the wheels. But the remarkable thing is that a riderless bicycle can do it too, if the design is right. The front wheel steers itself into the lean. Nobody is holding the broomstick. The broomstick is holding itself. And this is where it gets interesting, because the question becomes, what makes the front wheel turn into the lean? We have eliminated the gyroscope. We have eliminated the caster. Something else must be doing it. The answer involves mass distribution, specifically where the mass of the front assembly sits relative to the steering axis. And this is where the physics becomes genuinely beautiful, because the mechanism is so simple that you can demonstrate it with no moving parts at all. Imagine the front assembly of a bicycle. That includes the handlebar, the fork, and the front wheel. All of this pivots around the steering axis. If the center of mass of this front assembly is located ahead of the steering axis and lower than the rear frame's center of mass, then something elegant happens when the bicycle leans. Think of the front assembly as a pendulum hinged along the steering axis. When the bicycle is perfectly upright, that pendulum just hangs there, symmetric, no torque. But the moment the bicycle tips to the left, even by a fraction of a degree, gravity grabs the front assembly and twists it around the steering axis. The direction of the twist depends on where the mass is. If the center of mass is ahead of the axis, the twist turns the handlebars into the lean. To the left. Exactly the direction needed for recovery. You do not need to take my word for this. Walk up to any bicycle leaning against a wall. Hold the seat with one hand and tilt the whole bicycle to one side. Just lean it, not hard. Watch the front wheel as you do this. The handlebars will turn all by themselves into the lean. If you tilt the bike left, the front wheel steers left. If you tilt it right, the front wheel steers right. No spinning wheels, no motion, no speed. Just a stationary bicycle, responding to a lean with a steering correction, powered by nothing but gravity pulling on a mass that is offset from an axis. That is the mechanism that was hiding in plain sight for 100 years. People were so fixated on the gyroscope, on the spinning, on the dynamics, that they overlooked something you can see on a parked bicycle. Now, on a real moving bicycle, this gravitational torque is not the only effect producing the lean-to-steer coupling. The gyroscopic effect contributes too. The trail contributes. And there are additional inertial effects that only exist when the bicycle is moving. The front assembly has inertia, and when the bicycle is both leaning and moving forward, the coupling between these motions creates forces that also tend to steer the wheel into the lean. The full picture is dynamic and speed dependent. But the mass distribution is the overlooked member of the chorus. It is the one that most people never hear about. And it is the one that the Delft team used to build their impossible bicycle. With no gyroscope and no trail, the mass distribution alone, properly tuned, was enough to generate the lean steer coupling needed for self-stability. Let me try to build this picture for you more carefully. A bicycle, when you strip away all the paint and the chrome and the romance, is a mechanical system with 4 main pieces: 2 wheels, a rear frame, and a front assembly that can pivot relative to the rear frame around the steering axis. That is it. 4 bodies, connected by hinges. In 1899, a mathematician named Francis Whipple at Cambridge sat down and wrote the equations of motion for this system. Full linearized equations worked out by hand with pen and paper. And they are a mess. Even after you simplify, even after you assume the wheels do not slip and the rider is rigid and the road is flat, you end up with a 4th-order differential equation. 4 eigenvalues. Each eigenvalue tells you about one mode of motion. And depending on the speed of the bicycle and all those design parameters I mentioned, those modes can be stable or unstable. Let me tell you what the eigenvalues say, because it is one of the prettiest pictures in classical mechanics. At 0 speed, the bicycle is obviously unstable. It just falls over. All eigenvalues are in the wrong place. Nothing helps. This is not surprising. What is surprising is how the picture changes as the bicycle starts to move. There is a speed, a specific speed that depends on the design, below which the bicycle is always unstable. Any disturbance grows. The bike wobbles, the wobbles get bigger, and it falls over. For a typical bicycle, this speed is somewhere around 3 or 4 miles per hour. Walking speed. This is why it is hard to ride a bicycle very slowly. At walking speed, the bicycle is fighting you. The physics is against you. Your brain has to work overtime, making large, fast corrections with the handlebars, constantly catching falls that the bicycle cannot catch on its own. As speed increases, something magical happens. The weave mode, that oscillating wobble, begins to damp out. The oscillations get smaller and smaller with each cycle. By the time you reach a moderate riding speed, maybe 8 or 9 miles per hour, the weave mode is stable. The bicycle corrects its own wobbles. This is the speed where riding suddenly feels easy, where you can take your hands off the bars and the bike just goes. That transition from struggling to effortless is not a gradual change. It is a threshold. You cross it and the whole character of the ride changes. Above that threshold, there is a range of speeds, a sweet spot, where all the modes are stable. The bike recovers from disturbances on its own. It feels solid, planted, trustworthy. For most bicycles, this range is roughly from 8 to about 15 miles per hour, though it varies with the design. At higher speeds, the weave mode is very stable, wonderfully damped, but a different mode starts to creep in. This is the capsize mode. It is a slow, steady lean that builds over many seconds, very slowly. On an uncontrolled bicycle, rolling along at 20 miles per hour, the capsize mode means the bike will eventually fall over. But eventually means 10, 15, 20 seconds. An eternity. Most riders never notice it because they correct it unconsciously, with a slight shift of their weight or a tiny adjustment of the handlebars. The bike feels perfectly stable. In reality, it is slowly falling, and you are rescuing it without knowing. And then, at very high speeds, something strange can happen. The steering can develop a rapid shimmy, a high-frequency oscillation of the handlebars. 10, 20 oscillations per second. This is not predicted by Whipple's simple model because his model assumes rigid frames and ideal tires. In a real bicycle, the frame flexes, the tires deform, the spokes have their own elasticity, and these additional degrees of freedom can interact to produce oscillations that the basic model does not capture. Shimmy is a genuinely frightening experience. The handlebars buzz in your hands. The bike feels alive in a way that is distinctly unwelcome. Experienced cyclists know to grip the top tube with their knees and relax their grip on the bars. The shimmy usually damps out on its own once you stop feeding it energy through tense arms. The equations are telling us something profound. Stability is not a single mechanism. It is an emergent property of the whole system. You cannot point to one thing and say that is why the bicycle balances. It is like asking why an airplane flies. Well, the wings generate lift. But the tail provides stability, and the ailerons provide roll control. And the center of gravity has to be in the right place relative to the center of lift. Take away any one piece and the airplane still sort of works, if you redesign the other pieces to compensate. There is no single magic ingredient. The bicycle is the same. The gyroscope helps steer the front wheel into a lean. The trail helps steer the front wheel into a lean. The mass distribution helps steer the front wheel into a lean. And there are other, more subtle effects as well. The point is, the bicycle has multiple redundant mechanisms for producing the same critical behavior. Front wheel steers into the fall. If you take away the gyroscope, the others can compensate. If you take away the trail, the others can compensate. If you take all of them away except one, you can still get stability if you tune the remaining parameters correctly. That is exactly what the Delft team did. They killed the gyroscope. They killed the trail. And then they carefully adjusted the mass distribution so that gravity, acting on the off-axis center of mass of the front assembly, was enough to steer the wheel into the lean. It worked. The bicycle was self-stable above about 5 miles per hour. There is something deeply satisfying about this, because it means the bicycle is not fragile. Its stability is robust. It does not depend on any one trick. It depends on the cooperation of many small effects, any subset of which might be sufficient if the design is adjusted properly. Nature does this a lot, by the way. Biological systems, ecological systems, even economic systems, they often have this property. Multiple overlapping mechanisms that produce the same beneficial outcome. So if one fails, the system still works. The bicycle is a mechanical example of that kind of resilience. But let me come back to the rider, because so far I have been talking about a riderless bicycle. And most of the time there is a person sitting on the thing, and the rider adds a whole other layer. When you ride a bicycle, you are doing something extraordinary. Your brain is processing dozens of inputs per second. The angle of lean, the rate of lean, the speed, the road surface, the wind, and your brain is outputting precise torques to the handlebars that keep you upright. It is a feedback control system of remarkable sophistication. And here is a fact that surprises most people. You do not steer a bicycle the way you think you do. When you want to turn left, you do not simply turn the handlebars to the left. First, you turn them slightly to the right. This is called counter-steering. You push the handlebars to the right, which moves the contact patches out from under you to the right, which makes you lean to the left. Once you are leaning left, you turn the handlebars to the left, and you carve a beautiful left turn with the lean and the turning force in perfect balance. Every cyclist does this, every single one, and almost nobody knows they are doing it. If you ask 100 riders, which way do you turn the handlebars to go left, 99 will say left. They will be wrong. The initial input is to the right. It is so fast, so subtle, that the conscious mind never notices. But it is there. If you put instruments on the handlebars, precise torque sensors, you can measure it. The initial torque is always opposite to the direction of the turn. Always. You can prove this to yourself. Find a quiet road. Ride at a comfortable speed. And then, instead of thinking about where you want to go, pay attention to what your hands are doing. Or better yet, do not think at all. Just ride, and then afterwards try to remember what you felt. You will realize that to go left, you pushed slightly on the left grip, which pushed the front wheel to the right. The wheel went right, the bike leaned left, and then you steered left to follow the lean. Motorcycle racers know this explicitly. In motorcycle safety courses, they teach countersteering as a fundamental skill because at high speeds on a heavy machine, it becomes important to do it deliberately rather than just relying on instinct. Push right, go right is the phrase they drill into riders. Push the right handlebar forward, the bike goes right. It sounds backwards. It works perfectly. Because what you are really doing is not turning. You are falling. You are deliberately inducing a controlled fall in the direction you want to go, and then catching it with a turn. A Scottish engineer named William Rankine described this phenomenon back in 1869. This is not new physics, but somehow it remains one of the least appreciated facts about one of the most common machines on Earth. Why does countersteering work? It is exactly the same principle we have been discussing. You need to get the base of support out from under the center of gravity to initiate a lean. Turning the wheel right moves the wheels to the right, relative to the overall center of mass. Now the center of mass is to the left of the support. Gravity takes over. You lean left. Then you steer left to catch the fall, and you are in a stable left turn. The centripetal force from the curved path exactly balances the gravitational torque from the lean, and you hold a turn for as long as you like. Here is a beautiful test of this. Get on a bicycle and ride near a curb, with your wheels as close to the curb as you can get them. Then try to turn away from the curb. You will find it very difficult. Why? Because to turn away from the curb, you first need to countersteer toward the curb, which would mean steering into it. Your body knows this unconsciously and refuses to cooperate. You feel stuck, trapped. Your instincts will not let you do the thing that geometry requires. Riding a bicycle, it turns out, is controlled falling. You never achieve static balance. You are in a constant dialogue with gravity. And your steering inputs are the language of that conversation. Lean, steer, recover. Lean, steer, recover. Over and over, hundreds of times per minute, below the threshold of awareness. Your body learned this dialogue when you were 5 or 6 years old, wobbling down a driveway with a parent running behind you, and it never forgot it. What your body learned that day was not how to balance. It learned how to fall correctly. Let me take this one level deeper, because I want you to walk away with an understanding that is sharper than just, it is complicated. There is a beautiful concept buried in the equations that I think is worth pulling out. The stability of a bicycle depends on a coupling between two kinds of motion, leaning and steering. The bicycle has, roughly speaking, two important degrees of freedom. It can lean, tilting sideways, and the front assembly can steer, pivoting around the steering axis. These two motions are not independent. They are coupled. When the bike leans, forces arise that make it steer. When it steers, forces arise that change the lean. This coupling, this conversation between lean and steer, is the heart of bicycle stability. If the coupling works the right way, a lean to the left produces a steer to the left, which produces a corrective turn which straightens the bike. The system is self-correcting. If the coupling works the wrong way, a lean to the left produces a steer to the right, the bike curves right, the lean gets worse, and you crash. Every mechanism we have talked about, the gyroscope, the trail, the mass distribution, they all do the same fundamental thing. They create a coupling between lean and steer that has the correct sign. They all make the front wheel turn into the fall. They are different physical pathways to the same mathematical result. Think about it like water flowing downhill. There are many paths water can take down a mountainside, through a valley, over a cliff as a waterfall, seeping through rock as an underground stream, splitting into rivulets across a muddy slope. The paths are different, the mechanisms are different, but the driving principle is the same. Gravity pulls water downhill. In the same way, the gyroscopic effect, the trail, and the mass distribution are different channels, different pathways, for producing the same crucial lean-to-steer coupling. And if you block one channel, the water finds another. This is what confused people for so long. If you cancel the gyroscopic effect on a normal bicycle, the bicycle still works. And people concluded the gyroscope does not matter. Then they said the trail must be the reason. But cancel the trail on a normal bicycle, and the bicycle still works, because the gyroscope picks up the slack. Each mechanism, tested in isolation, seemed unnecessary. And from that, people drew the wrong conclusion, that one of the other mechanisms was the real one. What they should have concluded was that multiple mechanisms can each carry the load alone, which means no single one is essential. It is like a three-legged table. Remove one leg and the table falls. But a bicycle is not like a three-legged table. It is more like a table with 6 legs. Remove any one and it still stands. Remove any 2 and it still stands, maybe with a wobble. You have to get aggressive, removing several at once before it finally tips, and even then, if you redistribute the weight carefully, you can sometimes get away with just 1 or 2 legs in the right places. That is what the Delft team showed. They removed 2 major legs and compensated with a third, and the table stood. That is why the bicycle problem was so hard to solve. People kept looking for the mechanism, the singular cause, the one explanation. But the bicycle does not have one mechanism. It has a family of mechanisms that all contribute, in varying proportions depending on the specific design. And the elegant thing, the thing that Whipple's equations capture, is that all of these mechanisms enter the same small set of equations. They all appear as terms in the same mathematical expression. And it is the total effect, the sum of all the terms, that determines whether the bike is stable. Let me give you one more surprise. Even among bicycles that we call stable, the transitions between modes are not smooth. There are critical speeds where the character of the motion changes qualitatively. Mathematicians call these bifurcation points. Below one speed, the weave mode is unstable and the bike oscillates more and more. Above that speed, the weave mode is stable and the oscillations die out. The transition is sharp. This is not a gradual fading. It is a switch. One moment the physics is against you, the next moment it is helping you. And there is a deep result in the mathematics that I want you to appreciate. For a conventional bicycle with all the usual design features, there always exists a range of speeds where the bicycle is self-stable. Not every set of design parameters gives you this. You can design a bicycle that is never self-stable at any speed. But for the standard proportions that bicycle designers converged on through a century of trial and error, the sweet spot always exists. They found it without knowing it was there. Their hands knew what their equations did not. So let me step back and look at the whole picture. A bicycle stays upright because when it leans, the front wheel steers into the lean, which causes the bicycle to curve, which brings the wheels back under the center of gravity. This is not one mechanism. It is the result of several physical effects working together: gyroscopic precession of the spinning front wheel, the caster effect from the trail, and gravitational torque from the mass distribution of the front assembly. None of these effects is strictly necessary. All of them contribute. And the balance of their contributions depends on the specific design of the bicycle and the speed at which it is traveling. This was not understood until very recently. For over a century, people argued about whether the gyroscope or the trail was the explanation. Both camps were partly right and entirely wrong, because both were looking for a single cause in a system that does not have one. The equations of motion were written down in 1899 by Whipple, but they are fourth-order differential equations with many interacting parameters, and it took until 2007 for a fully verified canonical version to be published. And it took until 2011 for someone to actually build a bicycle that proved the traditional explanations were insufficient. Think about that. One of the most common machines in the world. Billions of people ride one. Children learn to balance on one before they can multiply single-digit numbers, and the physics of why it works was not properly understood until the 21st century. This is one of the things I love about physics. The everyday, the familiar, the things you think you already understand, those are often the things that hide the deepest surprises. You look at a bicycle and you see simplicity. 2 wheels, a frame, pedals, handlebars. What is there to explain? And yet when you really push on it, when you insist on a complete, rigorous answer, you find that the bicycle is a dynamical system of remarkable subtlety. 25 parameters, fourth-order differential equations, multiple interacting stability mechanisms, speed-dependent mode transitions, and we needed both advanced mathematics and precision-engineered experimental verification to finally crack it. There is a lesson here that goes beyond bicycles. In physics, we often make the mistake of thinking that simple objects have simple explanations. They do not. A soap bubble is simple to look at and ferociously difficult to describe mathematically. A spinning top is a toy, and its full dynamics involve some of the most beautiful and treacherous mathematics in classical mechanics. The three-body problem, 3 masses interacting gravitationally, has been open for over 300 years. The universe is not complicated in the way we expect. It is not complicated the way a tax form is complicated, with lots of arbitrary rules. It is complicated the way a poem is complicated, where every word interacts with every other word, and the meaning arises from the whole, not from any single part. A bicycle is a mechanical poem. Every tube, every angle, every distribution of mass is a word in that poem. Change one word and you change the meaning. Make the fork more vertical and the trail shrinks. Move the front hub forward and the mass distribution shifts. Spin the wheels faster and the gyroscopic term grows. Each change alters the eigenvalues. Each change shifts the boundaries between stability and instability. And yet, for all this complexity, the fundamental principle is simple. A bicycle stays upright because it steers into its falls. That is it. That is the one-sentence answer. The complexity is in the how. How does the steering happen? Through what combination of forces and torques? And the answer to how depends on the particular bicycle, at the particular speed, in the particular conditions. I find that beautiful. The what is simple. The how is rich. And the fact that engineers designed a practical machine over a century ago that exploits all of this physics effortlessly without any of them understanding the full story, that tells you something about the power of trial and error. The early bicycle designers did not need Whipple's equations. They did not need eigenvalue analysis. They just kept building bicycles, riding them, adjusting the geometry until they felt right, and the accumulated wisdom of a million small changes converged on a design that was, in fact, a dynamically sophisticated machine. Nature does this too. Evolution does not solve differential equations. It tries things. It keeps what works. And over millions of years, it converges on solutions that any engineer would admire. The bicycle was evolved, not designed. And the physics that makes it work was discovered long after the machine was already perfected. I want to mention one more thing, because it gets at something fundamental about how science works. For over 100 years, physicists and engineers argued about the bicycle. The gyroscope camp said it was the spinning wheel. The trail camp said it was the Castor geometry. They published papers. They built models. They argued at conferences. And each camp had genuine evidence for their position. The gyroscopic effect is real, and it does contribute. The trail is real, and it does contribute. Nobody was lying. Nobody was making things up. The error was subtler than that. The error was in the assumption that there had to be one answer. This happens in science more often than we like to admit. We are trained to look for causes, singular. One input, one output. This caused that. And often, that is exactly how nature works. The moon pulls the ocean and you get tides. The sun heats the equator more than the poles and you get trade winds. Clean, elegant causation. But sometimes nature works differently. Sometimes a phenomenon is not caused by one thing. It is caused by the cooperation of many things, none of which is sufficient alone, and any subset of which might be enough if the proportions are adjusted. The stability of a bicycle is like that. It is a cooperative effect. And the mistake everyone made for 100 years was looking for a hero when the real story was about the ensemble. I think there is a lesson here for how we think about all sorts of complex problems. When you find yourself in an argument about whether the answer is A or B, consider the possibility that the answer is A and B and C in proportions that depend on circumstances nobody has measured yet. That is not a cop-out. That is often how nature works. And recognizing it takes a certain kind of courage, because it is complicated is never as satisfying as I have the answer. So the next time you ride a bicycle, pay attention. Feel the tiny adjustments your hands make on the handlebars. Notice how at low speed you work harder, making wider corrections, your wrists moving back and forth in quick, jerky little flicks. Notice how, at cruising speed, everything smooths out and the bike seems to float under you like it knows where to go. That transition, that moment when the corrections get smaller and the ride gets easier, that is the eigenvalues crossing from positive to negative. That is the weave mode stabilizing. That is a fourth-order dynamical system finding its equilibrium right there beneath you, between your legs, carrying you to work or to the park or wherever you are going. You are feeling mathematics. And if you can, try this. At a moderate speed on a quiet, empty road, gently let go of the handlebars. Not a busy road, a quiet one, nobody around. And watch the front wheel. You will see it make tiny oscillations. Left, right, barely visible. Maybe a few millimeters of movement. That is the bicycle steering itself. That is the lean steer coupling in action. The gyroscope, the trail, the mass distribution, all of them working together in a conversation that has no single voice, keeping you upright without your help. People sometimes ask me what the most beautiful machine ever built is. They expect me to say the particle accelerator, or the radio telescope, or the clock. Those are wonderful machines, it is true. But for sheer elegance per pound, for the ratio of what it does to how much we understand about why it does it, I think the bicycle is hard to beat. 200 years old, 2 wheels, a frame and a chain, ridden by billions, understood by almost nobody. And the answer to how it works turns out not to be a single clever trick, but a chorus of physical effects singing together in a key that nature chose, and that we are only just learning to read. You have been riding on top of an unsolved physics problem your entire life. And the answer turned out to be not one thing, but many things, cooperating in a way that is more beautiful than any single explanation could be. If that changes how you feel the next time you swing your leg over a bicycle, tell me about it.